Been a while since I've been back at school. Now all the teachers were reporting back today. So let's see what we've got here. This is page 28. So this says, in the reaction above, the forward reaction is first order in both PCl3 and Cl2, and the reverse reaction is first order in PCl5. So we haven't discussed much about reverse reactions. You would have to remember that from your equilibrium topics in your previous course. Let's see if I can get this to look a little better. It's about as good as I'm going to get it, I think. All right. So if we take a look, suppose that 2 moles of PCl3 and 1 mole of Cl2 are mixed in closed container at constant temperature. Draw a graph diagram that shows how the concentrations of PCl3, Cl2, and PCl5 change with time until after equilibrium has been established. So basically, we know that we need a graph. What's going to go on the bottom here? Shows concentration with time. So which one of those is going to go on the bottom? Concentration or time? Right? Who gets to be the first one to eat? Maybe my volume's not up.
Concentration.
Concentration is going to go where? Y or X?
X.
Concentration is the dependent on this, right?
So time would be at the X because it's an independent variable.
There we go. Time and concentration. When we do this, we can just put concentration like that and polarity, because what I'm going to do is I'm going to draw on the lines like the name of each of these things. So suppose you have 2 moles of PCl3 and 1 mole of Cl2, and they're mixed. So that means up here, concentration-wise, if we're assuming the volume is constant, it's a container is closed, we probably want to try to be with the PCl3 twice as much as the Cl2. We don't have to put numbers on here or anything. But if we think of that as 1 mole and that is 2 moles, since these are both reactants, we know that the concentration of the reactants will go down as the concentration of the product goes up. So that will be the PCl5. So that will go up as the concentration of the reactants all go down. Now they will reach equilibrium, and we don't know the case of BQ, if you even remember that for this, they didn't give it to us. So we don't have to figure out whether or not there are more products or more reactants at equilibrium. It just says make it at equilibrium. So totally up to you on that. But that's the gist of it. You want to make sure that there's more PCl3 because they put 2 moles of that in there. Then there is Cl2. You want to make sure that the PCl5, I probably should have made that more like this or something like that, but it's fine. Again, we don't know at equilibrium what the deal is there. So if we take a look here, it says give the initial rate law for the forward reaction. So rate equals K. And then if you recall, we always deal with our reactants here. PCl3 and Cl2. So they did not give us any data whatsoever to work with here. So how will we find those orders? Well, sometimes it's easier than you think, because it says in this first line, in the equation above, the forward reaction is first order for PCl3 and Cl2. So those are first order. Again, we wouldn't have to write those because that inherently means first order. It says provide the molecular explanation for the dependence of the rate of the forward reaction on concentrations of the reactants. So molecular explanation, that means that we're looking at the kinetic theory here. So the dependence of the rate of the forward reaction on the concentration of the reactants. The higher the concentration of the reactants, the more collisions, thus faster reaction. According to the collision theory. D, provide a molecular explanation for the dependence of the rate of the forward reaction on temperature. Well, temperature is a measure of kinetic energy. So if their kinetic energy is higher, particles are moving faster. Therefore colliding more often. Since more particles are colliding more often, faster reaction.
Could you also talk about the energy of the collisions?
You got it. So not only that, but we also have an increase in activation energy or overall energy. How do we want to say this? Makes for more reactants having the required energy. Increase in energy makes for more reactants having required energy. Energy of activation. Thus, more effective collisions as well. And higher rate. So that's a quick review of well, we know that as time goes on, the reactants decrease, products increase. The order thing, if we double PCl3, that means the rate would double. If we doubled both of these, then the rate would quadruple. And it covered some of our ideas of how to increase rates of reaction. Let's take a look then at 1992. B. Move you guys down here so I can see this book. There we go. All right, H2 plus I2 yields 2HI. For the exothermic reaction represented above, carried out at 298 Kelvin, the rate law is as follows. So again, we are in first order of H2 and first order of I2. Predict the effect of each of the following changes on the initial rate of the reaction and explain your prediction. If we add hydrogen gas at constant temperature and volume, well, what are we doing to the concentration of the reactants? If if we add hydrogen gas at constant temperature and volume.
The rate will probably increase.
Right? If we have more reactants, that means more successful collisions. So the rate will increase. More H2 increases the concentration of reactants. And thus, more collisions. Let's put with reactants. More collisions with reactants. Why do we want to say that? Because collisions with products does nothing. More collisions with reactants, increased rate. B, if we increase the volume of the reaction vessel. Well, this is a gas, so if we're increasing the volume of that, that's going to kind of decrease the concentration. Since we're increasing the volume, there will be a decrease in the collisions. And decreasing the collisions will decrease the rate. Let's spice it up again, forward reaction. C, addition of a catalyst. In your explanation, include a diagram of potential energy versus reaction coordinate. So the big thing is that you have to say that introduction of a catalyst something about providing an alternate pathway or reducing the activation energy or the energy required. So adding a catalyst will, not with, will provide an alternate pathway. Therefore reducing the energy of activation. Since we reduce the energy of activation, that means that we have more particles with that required energy. Hence, the reaction will go faster. Boom. Did say provide a diagram. So this is cool. It says, it actually tells you what to make your axis. That's one of the things that you want to look at whenever you say it. Include a diagram of potential energy versus reaction coordinate. Well, normally we call this reaction progress. They call it reaction coordinate. So we want potential energy to reaction coordinate. And this is just your same old thing. You've got your products over here. I'm sorry, you've got your reactants over here. I'm ahead of myself. I want to talk about whether the products will be below or above the reactants. Anybody got some insight on that? So here are my reactants. There's their potential energy. Will the products be above or below the reactant?
Below.
We know this because of the fact that it says it is exothermic, right? So if we take a look, we're going to have our hump. And the delta H for this should be exothermic. And include a diagram of potential energy versus the reaction coordinate. So we should also go ahead and put in this as the uncatalyzed. And then dotted line is usually used to show the catalyzed reaction. So boom, boom, we've got the delta H in there showing that it is exothermic. All right, the increase in temperature. In your explanation, include a diagram showing the number of molecules as a function of energy. So if we take a look here, increase in temperature increases the kinetic energy. Therefore, more particles have the required energy or the energy of activation, thus faster reaction. And again, this is like the one before. You could talk also about the particles moving faster, so there's going to be more collisions. Any of those would work. Then we need our diagram. Again, they have told us the number of particles as a function of energy. Basically, this is that Boltzmann curve. So we basically start over here. We have something with some energy. And then we want to change that. So if we say that right here is our energy of activation or activation energy, then if we increase the temperature, remember that we still want a relatively same amount of particles. So what we're going to do is we're going to bring this curve down, but we're going to extend it out here. Go ahead and bring it down and extend it out. And what that does is that takes and gives you a larger amount of particles with that required energy. And if more of those particles have that energy, then that means that you're going to have a faster reaction because they already have what they need. So for tomorrow, I'd like for you to do 1987B on page 30 and 1980D on page 32. So again, this one is similar to drawing the things and with the more labels. A C may be a little bit weird for you, but we'll cover that tomorrow. For this one, basically you're finding the order using data. On the basis of the rate law determined, then you're calculating the K and specifying the units. This one might be a little tricky. What is the numerical value for the rate, for the initial rate of disappearance of C2O4? So if we take a look at this, we know that this is the initial rate of formation for Cl. We want to find the disappearance of C2O4, and it's in experiment 1. So I wonder how much space all that's going to take me. I'm just going to imagine that it's going to take me quite a bit of space. And to calculate this initial oxalate ion won't take me much at all. So if we take a look at this, what is the numerical value of the disappearance? Well, we know that this is the appearance, and we are doing experiment 1. So it's 0.52 times 10 to the negative 4th moles per liter per minute. And in reality, we can get rid of that minute, but let's just do molarity there. Yeah, we could just do molarity. And that is of Cl negative. Well, from this, we know for every 2 moles per liter of Cl negative, it only requires 1 mole per liter of C2O4. So again, that is just a stoichiometrical function of that, but it doesn't seem like that initially because you've got this graph and stuff like that. But if we read this, all it's saying is, hey, if we form this much of this moles per liter per minute, then how much of this must be disappearing over the same amount of time? And then you would take your 0.52 times 10 to the negative 4th and divide it by 2. I get a big little number, or actually a small little number, 2.6 times 10 to the negative 5th. And it's actually they give you a rate. So if we found this moles per liter, that would be moles per liter per minute. And you could put that back on there. Because they do want that rate, we would need that unit on there. And you can't see it, but there it is. Moles per liter per minute. All right, where are we at on time? $8.50. Oh, okay, we're good. I'm going to give you guys about 10 minutes to do those problems and the rest for homework, but I do want to show you guys something on the AP Classroom. Maybe. Get it, get it, get it. I don't know why it does this so much. This might look different than yours. Just to make sure, I just want to make sure that you guys have like the same type of stuff. So we are on unit 5. I have put on there, and I suggested even if I don't have these checked, that you guys go through these videos and then these topic questions. So I have suggested you to go through 1 and 2 is what 1 and 2 and 3 I think is what we've covered at this point. Later on this week we will be doing the elementary reactions and stuff like that. I don't know how that looks on yours, but hopefully you can see like it asks you to do that. We've actually covered collision model and almost all of the reaction energy profile. When we do elementary reactions, that will cover the introduction to reaction mechanisms and reaction mechanisms of rate law. Steady state approximations is part of that as well. And then the multi-step reaction energy profile is nothing more than basically 2 of those two of those potential energy to reaction coordinates, not much different. And we've already covered the catalyst. So we'll probably be done with all of this by next Tuesday, which then we'll give you the MCQ and the RFQ like we did with the last one. Now, the reason why I'm stressing these videos, and if you can go back to the previous units and watch these, is let's see if I can do this. That is my home. I don't want it to be my home. Is there something before this? So what they did is AP sent out a letter over break. And unfortunately, it doesn't look like they're showing it on here anymore. But it seemed to me that they were really stressing these videos and these topic questions. Let's see if this is it. Nope. Basically, what they said was that they were trying to give a schedule for people to get through all of the material by May 7th or whatever the day the test is. And they were like, look, if you do these questions, it kind of felt like they were really stressing these out. So if you don't have, like, if these aren't assigned for 3 and stuff like that, I'll go back and reassign them. I don't know if you guys can actually look at them unless I assign them. So if somebody could email me or something like that, I don't know how this looks on your screen. If it's blank and then you don't have it unless I assign it, I'll have to go back and then make sure I assign all of that. Because it does seem like they're really stressing those topics and these questions. And these videos, I mean, they're pretty short. They're like 5 minutes each. And basically it's teachers from all across the country or whatnot, basically going through a few things, and then they do a couple sample problems. Very similar to what we did today. Questions on that? Questions on the week? Questions on the schedule for today? All right, you guys have 15 minutes to get through page 30, 1987B, and page 32, 1980D. If you have questions, by all means, you're always welcome to stick around and talk. Otherwise, get out of here.